Alright, so example 7.4-1, so is friction a conservative or non-conservative force? So now we think about the friction. So case number 1 here in your book is going to consider a particle moving along a horizontal table in a straight line from position 1 to 2, and we want to know what is the work done by the friction force on F, and then letter F for friction. So every time we think about the work done, we do the same thing, your force and then time the distance, okay? So we're gonna bring the same thing. Again, friction is the opposing force, so therefore the direction is negative, yeah? Because your main force is going in positive direction, so therefore you're going opposite of that direction is negative. Some of the book you're gonna get negative is symbol, to go into that direction, and positive is the other one. So you have to make sure that you understand the friction is opposing the motion force. Case 2, you're gonna consider a particle moving along a horizontal table that changes direction to get from 1 to 2. So you have this and you have that. Yeah, so you go that way, and then of course you also go this way. So the friction is going opposite to the first motion. The friction is going opposite to the second motion. This is your first motion going that way, yeah? And your major motion is like that. And friction is opposing force of that. So what is the work done by the friction force as it travels from position 1 to 2 in the path shown? And here is your 30 degree, okay? I already showed you the main force, opposite friction, main force, opposite friction, and pay attention to your coordinates. And then of course we calculated going opposite direction of the main force is your friction. And we go cosine, adjacent, to that. Because this is your cosine theta. Because you're going this way, so that's adjacent to that angle. And the second one is going to go, from this to there. So at that time, of course, it's going to be opposite, opposite side of that 30 degrees, so therefore a sine theta, because your force is going this way, and your friction is opposite of that main force, okay? So these are all it's just telling you where you're going. You go from 1 to 1B, okay? And your main force is going this way, which is adjacent on the adjacent arm of the 30 degree. So we give that 30, cosine 30. And you go that distance, and your friction force is opposing to that main force. So therefore you write negative F friction, FF. So anyway, so we got that too, and put that in. You're going to calculate it, and you will get this, okay, 1.414. So that's the amount of work done by the friction force. So the work done by the friction force depends on the path that it takes to get from 1 to 2. See, depends on the path. So therefore it is a non-conservative force, which you can't take it back because it's been used up in that motion, okay? 7.4-2 is asking you a question: is the gravity force, is it a conservative or non-conservative? So you gotta think about whether you can take it back and store it. Case 1, so we're gonna think about this. Consider a particle, and it's gonna fall from position 1 to 2 in a straight line. So what is the work done by W, which is this guy? Just particle weight, of course. It travels from point 1 to 2. It's going this way, represented by the force aspect, which is velocity, showing where the main force is going down. And position change from here to here, about that. H, okay, your coordinates, X and Y right there. Now you're going to calculate your force and your displacement, which is h, okay, from here to here. And that's your work done along that y-axis. Case 2. Consider a particle that falls from position 1 to 2 in a angle, which is theta here. Yeah. So what is the work done by W from point 1 to 2? So every time we have theta, we have to think about the main force going which direction. Yeah. And it is usually represented by the velocity. And we go from here to here, from here, yeah, to here. So here our path is being defined with 1b and 1b to 2. And you also have the external force, which is here and then here, in addition to your weight. We're going to put that in. Your work done 1 or 2, going from here to here. First you go from here to here, and then from there to there. Yes? Then we're going to put that in. Your going from here to here, it depends on that angle. And the direction is adjacent to the angle. Adjacent means on that side. Yeah? Not opposite to the angle. Adjacent means on this side of that angle. So that's a cosine theta. And your force is W. And then your length is you go down h. And that h is not against that triangle. So you have to calculate that. Yeah? So that is again on h divided by cosine theta, which is your angle. Yeah? You will have to calculate with your opposite to hypotenuse, adjacent to hypotenuse, and you're going to get that, yeah, for this distance, which is going that one, yeah, if you want me to show you the path of that. So we're trying to get the length of that by using that angle and this h, okay? N equal to, we will cancel cosine, and you're going to get WH. And that's the amount of your work, yeah? And then, of course, going from here to there. And that would be 0 because that's completely 90 degree to, yeah, to this guy right there. So we get from 1 all the way to 2. You're going to add WH with 0. It's going to be WH. Why this is 0 is because of that direction, which is completely on the x-axis. And our net direction is going from here all the way down. Even though we stop here, of course, that way because of these two forces. But still, you're going that direction, okay? You can also calculate it by doing the same thing as here, yeah? And that would be the sine, yeah? Sine theta. And of course, you can calculate this length as well in order for you to put it into here. It's the same thing, yeah? And you will end up getting 0 anyway, even though you calculate that. And the next one is the work done by the gravity force does not depend on the path that it takes to get from 1 to 2, so therefore it is a conservative force. So here is the first path going that way. You get WH. Second, yeah, you still got WH. You're going that way, the path is. So you have just compared this path and then that path, yeah, because the resultant is this anyway. So since the work doesn't depend on the path, that type of force is called conservative. Yeah? So therefore the gravity, force of gravity is conservative, causing things to come straight down. Yeah? Mathematically, why is friction a non-conservative force and gravity a conservative force? So let's put it into mathematics context. So the friction force, you change direction. Gravity force is only one direction going. Yeah. Therefore, friction is non-conservative because it depends on the path, and gravity is conservative. Friction is non-conservative. Gravity is conservative because it doesn't depend on the path. physically, outside. In the real world, why is friction a non-conservative force in gravity and conservative force? Friction is going to dissipate the energy. Let's say the friction, even though it opposes the main force, it also dissipate as heat. So like the train track friction, the extra energy will dissipate as, or extra force, that you didn't use for the work to be done will be dissipated as force, or sometimes even sparks, fire, heat, form of heat of fire. So you can see it in the train track. They try to stop it, and friction acting that way, and you will see some sparks that's going to come out of it from the extreme heat. So energy will release in that way. That is what it's saying. The friction force dissipates energy in the form of heat. Then the gravity force conserves the energy. It never go wasted. It's gonna fall. If it doesn't fall, it's gonna take a place and stay as stored energy, which is change it back to potential energy. Okay, it depends on the height. And then we will get into potential energy. Of course, you go back to your Eureka video and find it, and potential energy will come on. Alright, potential energy, in this book they use V. A lot of the professor and many other books also use PE. So here V. In calculus, heavy book, they're gonna go a little bit different. Okay, so energy coming from a particle's position. So we call it position in the space. So the amount of work a conservative force does not move a particle to a new position. We are going to keep it in that position because you don't use it in the motion. Okay, so the amount of work a conservative force does to move a particle to a new position. Energy, you're gonna store it. So basically, you have a object, and it is maintaining a position in the space at a place. Okay, when it moves, to another spot, that potential energy that it maintains at this former position will change into kinetic energy and do that work. And that's what it's saying. Energy coming from a particle position. The amount of work a conservative force does to move a particle to a new position. This is new position. And when you get to the new position, it also has another different potential energy. It depends on where that position is. Okay. So conservative forces are gravity, and the other one is spring. So a spring like that, you stretch it and then you release it, it's going to go back to the same. When we say the spring go back to the same form, spring form, it means the entire thing is taking place in the space. So therefore it goes back to the same position in the space, even though its orientation, another aspect coming in, might be different. So you might pull a spring. If the spring is not attached to a certain thing, if you pull it and release it, it will bounce back to go somewhere. And it will change the kinetic energy and potential energy very, very fast to restore its own in a different position, but still restoring the force. Okay, so we will go back to gravitational potential energy. So if a particle is released at position 1 and allowed to fall to a position 2 at a surface, and you have a work, and that work is done by W. Now whoever wrote it changed to W. So your work U and your work W. So same thing. Like I say, many texts will go by W. So here is your height. So this is position 1 and 2. Your weight is going down. We have three different paths right there. So now we're going to calculate the work done. It's the same thing, W, and W is this weight, okay, and then of course H. in your W here, we just write down the mathematical formula for weight, which is mg, and then times the h. Okay. And you're going to get the work done from 1 to 2. Okay. Of course, right now she's using loosely weight as a force here. So she's using between F and W, so force and weight. Okay, it's the same thing. Yes. All right. Again, don't go into confusion with work and the force and the energy. They're different. Okay, and you know how they're connected. Depends on the which energy is it, the initial energy or the final energy. Okay. All right, and then we'll get into the next one, and which is your kinetic energy. So the energy stored by the particle at position. First, before we go into kinetic energy, we're going to concentrate the potential energy at point 1, yeah, which is this guy, position 1. So let's talk about that. So that is about h, okay, away from the position 2. So we're going to go mass, and then height, and then the gravity, yeah. So therefore you get mgh, and that is your first potential energy at that point. Here, of course, it is written generally. Yeah, you have 2 different points, so this you can change. Yeah, depends on the position. This h is going to be at that, or h is going to be 0. Yeah. Then we will get into gravitational potential energy. Well, your gravitational potential energy is the energy, okay, this little body or particle possesses because of the position, yeah, and that position again is confined to that gravity field. So like your Earth here, our planet, and then everything, yeah, on the Earth is subjected by this gravity. Of course, there's layers in the atmosphere that is protecting us from the space. Yeah, without this air, we won't live. Yeah, because the space environment is pretty harsh. A lot of forces out there that how this planet is sustaining this life, yeah, on Earth is incredible. Incredible is a miracle. Yeah, because this thing is withstanding so many forces outside. By the way, balancing, yeah, in the space, struggling to survive in the space, vast, huge space out there. Then we will get into 7.5-1. Can the gravitational potential energy be negative? So we have to think about, can it be negative? Meaning, like, can it go in opposite direction? Yeah. So you have your Vg, and then you're going to have a position 1 and 2, and then the 3. So when you think about it, we have, look at this height, yeah. So the height is going different, yeah. Different height. So from the ground all the way up about 10, at the ground is 0. Down the ground is going to be -5, yeah. And I mentioned in the lab to choose a ground is because of the gap, you know. So anyway, so if you can of course arbitrarily choose something above the ground by neglecting the whole thing, but it's okay. But it's good to use because ground is kind of like a reference point when it comes to the gravity potential energy. So here this is 0, 10 in height. Going down is a -5, yeah. So therefore, when you calculate it, you will get a negative number here, positive, and then 0 here. So therefore, yes, it depends on your origin choice. Yeah? So this is where me and a couple of students argue about it. So in physics, you will be taught, if you come from the physics background, you'll be taught it's okay, it doesn't matter, we can choose whatever the reference point is. Therefore, you can either choose this or you can either choose wherever you want to reference it. Just make sure that when you reference this, it would be gauged as 0. Then we will get into what if we change the location of our datum. So our reference point, we want to change the reference point. Can we do that? So now we're going to change. Let's do this thing 0. So it's go -10 and then -15. So we change the datum reference point. Then consider a spring. So we're gonna change the spring, and that is being stretched. And here it is a fixed spring because it's attached to this hook right here, and you're gonna make this change in distance that way. Here is the end stretch length, which is L0, O mean like origin. And here is your x starting point 1 and x ending point 2. Your force is going in that direction. Then we come to example 7.5-2. So what is the work done by Fs equal to k and then x? That's just showing you your force. It's going, we have a k coefficient of the spring, and this depends on the spring material, and then times your x. It's going to move the spring from position 1 and 2, and we want to find the work done. So we calculate, because we go into F, and integrate F according to your this mean like integration of F depends on change in your position R, and then you go from x1 to x2, which is this guy, and you calculate it, and you're going to end up getting this, which is very similar to your kinetic energy formula, which is 1/2 mv squared. Of course, thus your work done is 1/2, and then coefficient of friction times your distance, the whole square. So what is the elastic potential energy? So since the spring is going to restore the energy, we have to find out the elastic potential energy. So the elastic potential energy is 1/2 your spring constant times the change in the square of the position 2, which is this guy. And then we're going to calculate it. This guy is the potential energy. This is the work that we just did, and we're going to transfer that work to the potential energy, because this guy is completely elastic. So that's going to be 1/2 k and then a squared. Here, of course, we get rid of the position 2 right there. Since it is elastic, all you have to do is go back to this, restore that energy. So what's the potential energy at the position 2? So when you look at the position 2 here in this example, it is compression. We compress it, and your main force is going that direction. And of course, your original L is going to be 15, and you're going to compress it, okay, one moment. It is it's supposed to be this, supposed to be this guy is 25, and then this one is 15. Yes, so change it in your handout, and then of course you're gonna get your potential energy V, elastic because of the spring, and work done is 1/2 ka squared. We already translated from your work done to potential energy, and then we're gonna put to the position number 2 by using 0.1 squared divided by 2. Centimeter is a change into meter, and then of course you will calculate it and present that with in terms of k. So you will get 0.005 k. We're just putting the length into here, that into there when you calculate it. So where's the potential energy at position 1? So we calculate the same thing. When you get to the position 1, the potential energy is 0, because we're compressing from that position to there. So you're not storing the energy at that. It was just as the original position right there for it. So can elastic potential energy be negative? It cannot be negative because you have a constant 1/2. You have a constant spring constant, which is positive. So whatever that come, negative or positive, since you're squaring it, you will always get the positive. Yeah. So therefore, no. So even if x is negative, it is squared, creating with this mathematical operation, squaring it. So creating a always positive number. So what is the potential energy at position 2? So here is your position 2. You're going to calculate that. We already calculated position 1, so you're going to put that in, negative 0.1, the whole square. You're going to get that, the same thing. So I want to go back to make a point. It's just showing you it's the same thing. It's because you're storing the energy, because it is the same spring. Alright, so consider two identical springs. So this means that the two springs are made of the same wire, which is this guy, and have the same diameter. I've got that diameter right here, from here to there, and from here to there. And number of coils, and have the same end stretch length, which is this guy, which is equal to 10 centimeter. So during an operation, both springs work within their linearly elastic range. So the spring A is going to operate between 10 centimeter and 20 centimeter. So spring B is going to operate 15 centimeter and 25 centimeter, in which spring stores the larger amount of energy at its longest length. So we're given different length right there, and then we need to find and compare the energy. So the question is asking you at longest length. So the longest length is 20 and then 25, yes? So the spring B is going to store because it has a longer length. The second one is, what is that? That's wrong. Okay, so during the operation, both springs work within the linear elastic range. Spring A 10 to 20, spring B 15 to 25, and the question is which spring has the larger change in energy moving between its extreme operating points. So since they have the same, like when you look at it, it's just a 10 centimeter difference when they do going back and forth in between that two different position. So you will be getting the same energy, because they're moving only the same distance, which is 10 centimeter in spring A and B. Then we will get into work energy balance. So we go back to work may be broken up into conservative and then non-conservative work. And we have initial kinetic energy, final kinetic energy is equal to work done, to the initial kinetic energy. The second equation, you have an initial kinetic energy, you have a work 1 to 2, by the conservative, and then you're going to also consider work 1 or 2 on that path of the work done by the non-conservative, forces. So we will consider all of it in order for us to get the final kinetic energy. So non-conservative work is your potential energy, which is this guy, yes, right there. So non-conservative work, your potential energy, and we come up with equation, and we can be able to put the symbol for the potential energy. So we'll put that T is here and U is there, and you're gonna put V1 for the conservative potential energy. And this supposed to be potential energy is supposed to be non-conservative work. So I think they write it weird. It's supposed to be wrong here. Just make sure that this is non-conservative work, and that will be conservative work. Then we're going to get into where there are no non-conservative forces performing work on the particle. you're just going to go non-conservative. There is nothing, so therefore 0. And you're going to have potential, kinetic, and then potential is equal to kinetic and then the potential. That's the initial and that's your final situation. Of course, if you want to review your non-conservative forces, that you've got to understand that they dissipate, okay, as heat, sound, or deformation. They cannot be stored back, okay, so those are called the non-conservative forces. Especially, they dissipate the mechanical energy. And again, you're thinking about in a system, okay? The system can never be just a simple one in real life. They're very complex. And don't forget about the path, dependent. So work done depends on the path, not just the start and the end for the non-conservative forces. And you cannot recover your energy from the non-conservative forces. So like your friction, your air resistance, your tension in the ropes when you are slipping, apply forces and your normal force, okay? In some context, of course. All right, then we will get into, I'm falling asleep on the next one. Okay, so two metal balls have the same size, but one weighs twice as much as the other. So the balls are dropped from the roof of a single-story building at the same instant of time. So we're going to assume there's no air resistance. You're going to identify which of the following are true. So the very first one is the lighter the ball will reach the ground with more kinetic energy. That's not true. It doesn't matter light or heavy. It has nothing to do with your kinetic energy, because your kinetic energy. So why this is wrong is, if you think about lighter ball means you have not much potential energy, and you have also not much kinetic energy at the bottom. So this is wrong. It's going to reach the ground with less kinetic energy because it is lighter, because your kinetic energy depends on the mass, your half mv squared. And of course, the second one is what is this? This is the heavier ball will reach the ground with more kinetic energy. That is correct, because kinetic energy is directly proportional to the mass. So the heavier the ball, it will get to the ground with more kinetic energy, because you have a greater mass. So you're going to have a more potential energy and therefore more kinetic energy when it hits the ground. See, both balls will reach the ground with the same amount of kinetic energy. That's wrong, because you have different masses, so therefore you have different energies. The lighter ball will reach the ground, okay, faster. That is also wrong, because acceleration due to gravity has nothing to do with mass. It's the same. But then E is the heavier ball will reach the ground faster. Again, no, both will fall at the same rate with no air resistance, because it said it, so there's no air resistance. And then the F is both balls will reach the ground at the same time. That is correct, because in the absence of air resistance, you have different objects, but they're going to fall with the same acceleration due to gravity, because we said it is 9.8 meter per second, or 10. You can calculate approximately about the same, regardless of your mass, okay? Because your time is going to be square root of 2h by g. Okay, then let's go to conceptual example 7.6-1. So we have mass here, and then we have another mass right there. And of course, the position 1 here and position 2 is about h away from each other. And we calculate the v is equal to the square root of 2gh. Okay, and I gave you this equation for your lab. So it came from mgh is equal to 1 by 2 mv squared, because that's your potential energy and that's your kinetic energy. So the energy transfer from the potential to kinetic. And of course, this one is for that mass, because you have 2 times of the mass, bigger, and heavier, of course, and 1 by 2 mv squared. And so if you calculate v2, you will get this, 2gh. Your initial kinetic energy is 0, and then your potential energy, that was because it was at a height, and then final kinetic energy, you have it because it gains velocity and move, and final potential energy, you don't have it because it lost the ground, it lost this height. Okay, so 2 identical balls, they are released from rest, at the top of incline. They're identical except for the bump here. So your bumps shown in the accompanying figure, this guy. So we're going to assume air drag and friction are negligible. Identify which of the following statements are true as the balls arrive at the bottom of the incline. So we have these. Alright, so the very first one is ball A, and it says it's gonna arrive first. Okay, that wouldn't be right, because of this bump right here. So when you look at it, of course, there's no reason that this ball A will be faster, because when you think about the energy, it's completely conserved, and your path B is gonna allow acceleration, because of this steeper dip right here. Meaning, like, you experience acceleration because it's gonna go down and come back. So there will be a change of velocity. This guy is going up and then down here. And of course, this one, when it goes down, it's gonna go up. Actually, it will increase the acceleration, because of the steeper dip right there. So therefore, and which is better, for B to gain faster speed to get to the end faster. Because that one, you have to spend energy to climb up the hill and then come back down. This guy is just going down the hill, so it actually gain more energy and then go up. So when you think about the conservation, because when you think about the A very carefully, well, definitely slower than B, because the energy, if energy is conserved in this situation. Of course, B, so ball B arrives first. So when you think about that, even though it has a steeper dips, you tend to think that it could go, but it's the same reason. Okay, you have the same energy and the path. The differences is it won't cause it won't cause this to get to the end fast, right? It's because of the energy conservation, because it's gonna go down and then conserve back when it go up. So they got compensated at that dip. Okay, even though it gets a little bit more acceleration, the same thing is gonna go up and then conserve back going down. So you have a switch in KE and your PE, which is your kinetic energy and the potential energy. So they're gonna arrive at the same end. I would say, I was wrong when I was looking at this because of the way that it is going a little bit down here. Yes, it's gonna arrive at the end at the same time, because I would just say, like, expand the energy to go up, and it's conserve back because it's go down. Yeah, let's just take it like approximately, not to go into details. The same thing is going to go down, and then you're going to conserve the energy back, so they will get to the point at the same time. So this is correct. Okay, so that's wrong. Sorry, we have to think a little bit. All right, the other one is a ball A is going to arrive with a higher speed. Yeah, so when you think about that, it wouldn't be right. Yeah, because of the path. Yeah, it's going up and then and down. So ball A is not going to arrive with a higher speed. It can be. It's because the speed, depends only on the height and the gravity, not the path taken. Yes. So now we're subjected to the path only in this question. So no, this is wrong. And ball B arrives at the higher speed. That is also wrong for the same reason, because your final speed is based on the energy conservation, and so you're both okay. They come actually about the same height to me. Yeah. So your height you can calculate like this. Since they started from the same height, your question said it so, and they get to this point at the same time. Yeah. So therefore B, yeah, it won't arrive with a higher speed, because the speed again depends on the energy conservation. Yeah, and it is energy is conserved, so therefore both balls will arrive with the same speed in this example. Okay, when I look at it, my eyes vision is not very good, so I feel like slightly different, but it's okay. We can just take it like they're depending on the path, and they're at the same height and get to the same height at the end. Okay, so therefore they're gonna arrive at the same time with the same speed. Yes. Then let's go to the next problem, and this one is the cards here, four of them shown, initially move on a smooth horizontal surface and then up a short incline, go up, yeah, go like this and then up. So assuming the negligible friction, we're going to rank the cards from greatest to least achieved vertical height given the weights and the velocities as shown in this example. This one you have to calculate, because you are given C pound, and then of course that's the weight, and then the velocity, and U.S. customary unit system, which is your feet and your foot and pound. Yeah. So we have our kinetic energy and potential energy. They are the same because you're going this way and then you go up. Yeah. Therefore, we can be able to use this. Of course, this comes from the kinetic energy initial, and final. You add them up, and then initial, of course, and the final. You add them up, and then you cancel. You cancel right here. You don't have the potential energy. Right up there, you don't have a potential energy. Yes. So don't forget that it came from this. I'm gonna write that back down for you. Okay, so you're seeing that, and of course you cancel this, so therefore you're left with this. Okay, and that's your initial kinetic energy and the final potential energy because of that slope. So we're gonna put that in. That's 1 by 2 mv squared, and that's the mgh, and that's 1 by 2 is 0.5, and then we will put in each velocity and calculate. And then of course on this side you have a gram, which is a different gram right there for each situation here, and then times the height. Okay, height is not given to you because it's the same height anyway. So after you calculate it, you're gonna get this guy has the greatest value, followed by B, and then followed by A, and then followed by C. Of course, if you calculated, I'm just gonna do it by mind. So that would be like 4, 4 times 4 square, yes. is gonna give you, and then times 0.5. Your 4 squared is 16 in here. Yeah, I only calculate this, but the rest of them are the same. So, B is 9, but it's 3, and then of course your A is 4, and then this is 1. Yeah, so that's how we calculate. So you have D followed by B, and then A, and then C. Yeah, because 0.5 is the same in all scenarios, G is the same 9.8, and then H is the same height. What we're calculating is this height. Okay, it depends on, of course, when I say the height is this, slope height is the same. Since slope height is the same, in order for this thing to go up to a certain height, depends on this and this only, because G will cancel out, that will cancel out. Yeah, so all you have to do is just calculate V squared, and we get that. Yes, when you compare, you cancel things that are the same in your equation. If you cannot do it by mind, you can calculate it, yes, and you will get a different H, and you can also calculate that as well if you want to. But for S, we usually cancel everything that is the same, and we calculate only that is different, and we use directly proportional to H. Yeah, so therefore if this is big, H will be bigger, and we don't really calculate the exact amount anymore. Okay, when we do in the mind, we only calculate the we go by the directly proportional. So like H is directly proportional to B squared, like that. Okay, that's how we do the calculation. All right, then we can go to example problem. That's just the work, and here is kind of like a review. The slides are. So this is just showing you the warning here. This is the work equation that we use throughout the book. So all of the forces acting on a system may not move through the same distance. Okay, because you have a different forces at different angles. You know, so that's what's telling you about. And then because we come into kinetic energy, again, don't forget the system, yeah, and the sum of the kinetic energy of each particle, and this I is telling you to do that. So, and this is the sum, which is talking about the total, yeah, or the net of kinetic energy, and it's just showing you a different, situation here for you to understand. But all you need to understand here is, if you get like kinetic energy of the system, is we're gonna just sum it up, yeah, all of the kinetic energy for each particle in the system. If you think about the system, is very complex, yeah, even for us trying to use a particle to represent the whole thing, yeah, sometimes we do that. It can be accurate. So anyway, so let's go back. So potential energy of the system, we use these, yeah, is the sum again of the potential energy, again each particle, and that's very, very powerful, by the way. Yes, and it's so easy to write it, but it's so difficult, by the way, to study each system, because the number of particles, there are a lot of them, yeah, so therefore we will have to take a particle in a location and represent all the rest of them. It should be about the same. And potential energy of the system, again, the sum of the potential energy of each of the particle, and we can also write it this way. This is your spring, yeah, spring system, which is elastic. Then we go into work energy balance. This is kind of like a review for you, giving you all the equations that you need, and this is your work energy, your kinetic, your potential, and then your non-conservative work, yeah, is equal to your kinetic final, and then your potential final. Then here are kinetic, and potential initial, and then of course your final. They stay in a conservation of energy way. Then we come to power. Power is you calculate, because we want to get the rate, yeah, at which your work is being performed. So if you want to know what rate your work is, then we calculate power. All you do is differentiate your work yeah, in terms of time. Because every time we think about the power, we want to know like what is the amount of work you can do in a particular time, and then you compare it so you know like who is more, or which situation is more powerful. Constant force, if you have like a constant force, yeah, your power would be like that. So you can calculate power simply by multiplying the constant force with a velocity. Okay, so it came from your work, and then your force time your displacement here. Yeah, so r is in your coordinate system. So anyway, this is your distance. Yeah, distance and distance and the force is going to give you the work. Yeah, these are just a mathematical operation for differentiation, because we're looking at a different distance and different work. And of course, you have your power. Yeah, you can calculate this way. So now we are going to plug it in, this thing into here, du, and you will get that divided by dt, calculated, and that is this, and this dr, yeah, divided by dt is your velocity, because velocity is distance over time. We write it this way, yeah, in an easy way, but of course when we want to differentiate, then we write it this way. Because some students have issue if we try to write it in a compact way like this, yeah, but it's the same thing. Units of power will use joule per second, watt, yeah, horsepower. There's a foot pound per second, BTU, British thermal unit per hour. Yes, so these are all the your power units. So your word is joule per second, and W. Horsepower is HP, and we have conversions from word to foot pound per second, or BTU per hour. Yeah, and here is your power formula, and you have this power is force times velocity. So machines, if you think about the machines in mechanical world, they are designed to perform work, because we want the machine to do the work, because we can do the work. Yeah, so at a specific speed or over a range of speeds. So power curve for a typical gasoline engine. So this is your gas engine. It's just showing you how the power is relating to speed, okay, and then torque, and then of course your fuel consumption in your car. Okay, it might be a little bit difficult for you to read it because of the overlaps data that we show in a graph, yeah, visual graph. It's just you can see that the power is going to go up and then come down, and thus your speed as you drive, your speed go up and down. Yeah, your power is going to go that way. So if you study the power against a specific fuel consumption, you can be able to see it. Yeah, it's go up and then it's also go up. So that's directly proportional to each other. And then of course the torque is going to go that way, and then the specific fuel consumption is going to go this way. All you have to just read, this, if you go against power and speed, then you're going to read that line like that, and depends on the line, you can see whether it goes down or it goes up. Okay. Efficiency. Efficiency is very important in manufacturing world that you are in, because we make the machines to do a lot of the manufacturing, because human cannot be able to do it. We might be able to do it one day, but not every day, making the same thing. That's mundane and it's so tiring, so therefore we gotta bring in mechanical machines. So every machine has losses. We loss in friction, material deformation, your wear, your heat, your chemical conversion, your magnetic losses, and your electrical losses. So these are everything that we think about when we calculate efficiency. So efficiency, the power out, okay, divided by the power in. Efficiency, in order for you to get the efficiency, you have to calculate the power in and power out. And then you're going to divide power out by power in, and you will get your efficiency. Machines, they're not perfect, because they are a system. Every time you make a system, it isn't perfect. Every time, it's like a group work. You're individual. You have your own efficiency, but when you work with other people, your efficiency goes down because you have to adjust yourself with other people's characters. Characters. Like work ethics and things like that. So when we think about the machine, the same thing. They're in a system. The machine system inherent error is there. So therefore, machine is not perfect. Meaning like your efficiency can never be can never be equal to 1. It would be less than 1. As soon as particle aggregation became forming a bigger aggregations, and bigger aggregation form a solid aggregation, and solid aggregation form some form of a system, you're gonna get your efficiency go down. All right, we're done for this chapter. So that's it for chapter 7. Of course, we have like 3 different parts on it, but I think it should explain enough for you. You can just go little by little for each video if you care to listen. If you don't care to listen, that's okay too. Who cares? But highly recommend you to listen because I explain that to you in details. More than what your course covered. Okay, that's it for today.